So I said, that's when my daughter got sick. I see it.
I'll go get like, I'll go get some orange juice, and I'll keep up my vitamin C. I'll be fine. Right now. Yeah.
That I don't get sick.
Oh my
I
God.
think this is
Feel sick? I'm gonna take it.
I know, yeah. 'Cause everyone around-
this is the season. I think Thanksgiving makes it worse as people travel home to go see family, and then you come back for Christmas. So I feel like from now till the end of the semester, I get a lot of absences, and I think it's mostly due to illness. So just take care of yourself. Keep doing your vitamin C. Yes. I'll keep recording my stuff to try to help you when you're sick, that you got a resource. But yeah. So I'm going to move into the metric ones. And Abby already pointed out that maybe there's some confusion on how to do these thread notes for these because maybe they don't give us all the information we need. So I'm going to build them with what information I'm given. So kind of like here, I really didn't build this out any further. I know, so when we finished this last one, I kind of figured that I only did like 2 columns of thread node data. Where on this first question, I was kind of doing like 3 columns of kind of thread node data. So if I'm not given like this class of fit, I think I can just leave it off. And it's going to be kind of a simplified thread note. So with these metric ones, we're not given an explicit like class of fit. So we could either invent it or we could just leave it off. But I'll talk through it. But it's going to be built kind of the same way. I'm going to need to look at that metric, the metric sheet from my appendix B. I'm going to look at this as major diameter. Maybe we can make sense out of this, but just remember you have that page 358 I used for the first couple, or yeah, for like UNC or Unified National type fasteners. I was using page 358 of the book of your textbook, chapter 11. Now I'm going to use 359. It's got the metric, just the next page over is how these thread notes are built. And so in the textbook, it kind of letters the steps A through F on these. M is the symbol. So like the first part of your thread note is going to be just a total straight up copy of the major diameter here, which is considered an M. That's an M3. So M is always going to be the first indicator of a thread note for a metric fastener. And that's nice because it's like a quick, hey, this is metric, right? Like I get that UNC and UNF kind of cues me in. Plus it's in a fractional form as a major diameter. That cues me in that it's this unified national type system. An M in the front is just my Q, and then I'm in the metric mode. And then when I see a 3, I instantly think of millimeters. And so that's going to be like a 3 millimeter major diameter is what that is telling me just by having that. And then it'll be the same way. It's going to be like another column of classification status, and it's a course. So now I need to kind of reference maybe my sheet. So let me go over to Appendix B. So so in your textbook, they kind of consider this as like the A step is figuring out if it's metric or not and applying M or not. And then the B step is like what the major diameter is. So in your textbook, this is kind of like A and B steps. C steps is going to be the thread pitch in millimeters. And then we're going to follow that by a dash. So it's similar, only, we were looking at threads per inch in a unified national classification system. Here we're actually going to look at pitch is what's going to be explicitly being, so it's actually given us kind of the math or whatever. It's not giving us threads per millimeter or threads per whatever. It's going to give us the pitch in a metric fastener thread note. And so if I go over to the same thing, so this is the page we worked on. I think the next page is metric though, this one, yes. So I'm looking for an M3 in course, right? So I've got here's kind of my nominal sizes essentially kind of column. I'm going to have my tap drill diameter, which is if I have to cut internal threads, that's where that column comes into play. And then for coarse, and then I have some fine threads as well. So this is kind of a different chart. I guess these are our nominal sizes. We've just got coarse ones here. And then we don't even have the option to have fine threads on this chart until we hit M8s or larger. M8s, M10s, M12s. They skip a few of the oddball sizes. So it's just the way that these metric threads were organized when we created a system essentially. So I'm an M3. So an M3, if I look here, I either have an M3 or an M3.5. So these are mine's an M3, 3 millimeter. So this is the next one by this is the pitch. So I don't use this. This is the thread note doesn't have like an X in it, like M3 by 0.5. Just this chart does. And it tells me that, hey, those are by 0.5. Uh, that's the pitch of this particular thread. So. And I wouldn't even have that option for a fine thread. So coarse is the only one. So to me, it's going to be M3 dash 0.5. So I'm going to go back to my worksheet here. Yeah. M3 by 0.5. And then that's all the information we're really given. I mean, in order for us to give a thread note for this, they've only given us this two information. The next thing they could have given us was whatever was going to go in the next column over of classification, which is similar to standard, where we up here we had a 3B, 3 being like for a really fine fitting relationship, and B is X internal threads, and 2 is a general purpose fit, and a external thread for A. They kind of have a similar system here, but we aren't given that to be able to determine it. But in your book, page 359, it does say that that's kind of what they call step D. And I'll just read it again just so it's on my because we talked about it maybe on the I don't think I'd stopped my video before we talked about this, but step D in your book says the number can be a 3, 4, 5, 6, 7, 8, or 9, which just means to me in the Unified National Course, I either have a 1 through 3 fit relationship. In the metric system, they have a much more refined system, but it's 3 through 9 they could designate as the class of fits, whether it's a coarse or a fine kind of fit. Not necessarily a coarse or fine thread, but just the fitting relationship, how tight or loose the tolerances is on those parts fitting together. With the larger number, so let's see, our grades 3 through 5 are fine, and 7 through 9 are coarse. So that's also kind of backwards from Unified National Course System, right? Because it was like 1 for loose, 2 for moderate, and 3 for a fine fit. Here, it's actually 3 through 5 are fine, and 7 through 9 are coarse. So it's just opposite. That's additionally confusing for sure. It's like flip-flopped of the Unified National Course System for metric. The lower the number here in a class of fit, is the finer, and the higher the number is the coarser, with 6 being the general purpose. So whereas 2 is the general purpose for Unified National Course System, 6 is kind of the general purpose for a metric fastener. And then it's dropped here because we don't even know that. But like if I was doing it for a general purpose, it would be like a 6 for general purpose. And then I would have to follow it by, in the Unified National Course System, I'd follow it with either A or B, external or internal. Here, they use capital letters and lowercase letters. So capital letters here, and they'll use a G or an H. And I don't think it, I don't, G means a tight allowance, and H identifies with no allowance. Oh, anyway, that's weird. So the first letter is internal threads, use uppercase. Maybe I had that backwards when I was saying it before. But if I'm using an uppercase letter, it's an internal thread. And if I'm using a lowercase, and then in this case, this is an external thread. So it'd probably be a 6H with in lowercase though, H like this. I'm not going to put this column because I wasn't given like to even evaluate its fit type like I was up here. This one had a fit, class of fit. Yeah. Yeah, lowercase means, yep, external. Uppercase, if this was an uppercase like this, that would designate that it's an internal thread. So I feel like I kind of feel like it's unfortunate we weren't evaluating that category here because it's kind of showing a shorthand notation, and you really can't identify like if this is all you're looking at and you're not looking at an actual imagery of the part on a print, like you would either see a bolt or a threaded hole or something, that's easy to make sense out of it once when it's like a local note pointing to that on a drawing. You don't even need that third category because you can just tell, oh, that's a bolt. Oh, that's, that's an external thread. It means, oh, that's a hole in a plate. That's an internal thread. So you almost don't need that classification when you're looking at a drawing. But if you're not looking at a drawing, you don't know, right? Like, so this being if I'm just looking at this written notation on some chart like I'm looking at now, I don't freaking know if that's internal or external unless it had the classification to fit with it. So, and I would guess that in some industries they're really particular that you carry the full thread note, and in some cases they get real lazy and they leave shorthand notes on their drawings or even in their tables of charts or whatever. So you just kind of have to be like, I don't know, ready for whatever your industry that you work in and whatever how strict of a standard they follow versus how kind of loose they follow. But I'm going to kind of go loose here in some ways. I'm just going to be like, I'm only going to evaluate this to 2 columns of thread notes. It's an M3-05. That's a 3 millimeter major diameter with a 0.0 or a 0.5 pitch. So I can still figure the minor diameter here. I think it's a little different constant multiplier here though. So I can still kind of figure out, it does tell me that it's an external thread. So it would probably be a -6 little h, but I'll just leave that off. And from the minor diameter, I can figure it out using this. So it's going to be a 3. So I'll pull up my calculator and run that. I look at it as being, clear this out and say it's going to be 3 minus this little equation here, a 1.2075 times the pitch, which is 0.5. So this should be what my minor diameter turns out to be. And obviously it should be less than 3 millimeters because I've got to be able to like cut threads with it or whatever. It's going to be 2.39. So I'll probably just go to 2.4 on this. If I hold it to, I don't know what I did on my actual answer sheet, but I carried that to 4 decimal places actually. 3963, 2.3963, I guess is what I'll write here. So I did carry this. Not that it super matters. I don't think I say explicitly how far to carry it, but 2.39, 3963, I think if I was rounding, right? Is that right? 3963, yeah, something like this. I guess that's my minor diameters in millimeters. Yeah. And then threads per millimeter. I kind of can figure out as like threads per inch, but you can be like threads per millimeter. Well, I'm just going to do 1 millimeter divided by the pitch. So I'm looking at just 1 millimeter, not 1 inch here. And whatever this equals is going to be my number of threads per millimeter. So 1.5 divided by 0.5 is 2. Is that right? Yeah. You need to do that. Do it on your calculator. 1 divided by 0.5. Yes, 2. So this really has 2 threads per millimeter, which makes sense because they're 0.5 millimeter pitch. And that's all that it needs right here. Like I say, some of these might be blue, some of these might be black, depending on how I haven't formatted it all to be the same color. Okay, so what's the next one? M1.6 and its course. It wants to know maybe one more, maybe a little, it wants to know the tap and drill size. So let's look at that. M1.6 is already small. That's a 1.6 millimeter major diameter. So I know it's going to be like an M 1.6 by whatever the pitch is of that. I don't have that memorized. I wouldn't even know. So I go to my chart and I look for 1.6. It's the very first one on the list. It's only coarse. 0.35 is the measurement. 0.35 millimeters is one pitch. And that's really all I can evaluate to, just 2 columns there. On that same chart, it probably does have the tap drill size, or which is the drill size I would need if I was going to cut my own threads, is what I think about. So this is going to be a much smaller, should be a much smaller diameter than the 1.6 in order to cut threads. And these are internal threads, so this would end up being with a capital H to show that. If I was really finishing the third column of the thread note, it might be a 6 with a capital H to designate that it's an internal thread situation. But let's see. This kind of gives it away. Essentially, with internal threads, we're usually wanting to know how big we can make the hole in order to cut thread. So why this shows up in this category is kind of because it's an internal thread. What does it say it is? Tap drill diameter. I'm going to drill with a 1.25 millimeter kind of diameter drill in order to cut that 1.6 threads. So 1.25 is going to be my drill size. So I'd have to have a metric set of drills. That's the other, we were talking about that just off camera, is that in order to make holes, there are a lot of different designations of drill bits that do that or tooling for that. They're fractional, they're numbered, they're letters, they're also metric drill bits. So it like a machinist that's making fasteners and threaded holes for fasteners to go into, the amount of bits they have access to is probably a pretty extensive little catalog of bits because there can be hundreds, if not thousands, of different thread fastener relationships, and they have to have the drill bits to do those, and not just one that's close enough. They need the actual one. I mean, they might be close enough in some general purpose applications of threads and fasteners and relationships, but if it's a real critical application like aerospace or something, that you can't be close enough. We have to use the engineered hole size to match the thread size. So this is really critical. 1.25 is what I need to write on my chart here. So can have major catastrophe if things aren't exactly sized right. So I always forget where this one is a 1.25 millimeter drill bit to use to bore that hole. And then the threads per millimeter will be the same way here. If I'm 1 millimeter, I'm going to divide that by the pitch 0.35. And that should be my threads per millimeter. 1 divided by 0.35. I get some weird odd number probably. 2.86, I guess I'll round this to. Why I didn't round to 4 decimal places, I don't know. I do random things. 2.86 threads per millimeter. It's the unit of length divided by the pitch. Kind of same up here, except for the unit of length was like a 1 inch per threads per inch. These are kind of 1 millimeter and pitches per millimeter. Gives me threads per millimeter. What's that? Is yours writing superscript?
Well, on the page on the chart.
For this M27? Oh. Okay, let me look on the chart itself, this one. M27. Oh, yeah, B. Only for high strength structural steel. It's just like a footnote. Yeah. It's a footnote saying that, hey, if you're using that thread, that's only for high strength structural steel fasteners. So, there might be, that might be a note that'd be like, oh, wait, if that's not my application, I probably shouldn't be using that fastener potentially. It's like a footnoted fastener. I don't know why. I guess there's a few of them that way. M27's pretty large, but what's that? Yeah, I don't think so. I don't think you need to worry about that. Yeah, I guess that's just a little footnote to know that, hey, that's for that specific application, high strength structural steel fastener. Probably anytime I'd see that, I'd be like, that means that's an expensive fastener. So if I didn't, that's probably the major reason why I would want to know that. And I'm buying a way more expensive fastener than I probably need. So, however, that's the only one in that size. So it's kind of, well, I could get a coarse one that is. I could get a fine fastener in an M27 that's not designed for a specific, a real specific application, I guess. And it's probably a lot cheaper. But it's a fine thread. Maybe it's not what I want, but I don't know. Yeah, what else? So we got a few more columns, got lots more, right? Sheesh. How many more do I got? Whoa, this can take me forever. Not really. Let's see. I think I'm getting faster in my stuff. So let's see. They're all just a little bit different though. So this is a hex head bolt. And so, oh yeah, so this is going to be related to how I'm going to fill out some of the necessary information for when I go to draw it actually. So I like it now. This works us into some similar stuff, but now we're going to worry about some dimensions of that hex head bolt. So let's see. It's not asking me for thread notes here. It's just asking me for some specific information about this. This is a hex head bolt. It's 1/4 inch. That 1/4 inch that I was given means that is the major diameter. So it's a 1/4 inch here, not 1.4, but 1/4 I like. So then I need to know, okay, this is actually some drawing information, or it might be if to know the width across the flats is helpful if you know to go grab the tool out of the toolbox to actually like tighten or loosen a 1/4 inch, what we would call as a 1/4 inch bolt here. And they will use like bolt and screw pretty much interchangeably in a lot of like designation. If you're looking through like manuals and stuff, they can still call a bolt a screw. Like a machine screw can still be considered a bolt. Like I feel like there's some like crossover in terminology there. We might consider it a bolt. Somebody might say, "Hey, that's actually a hex head screw." We're talking about the same thing. But so just be aware of that a little bit. Bolt is maybe like a more generic term, and maybe the more correct term is probably a hex head screw or the other or a flathead machine screw. It really is just the threads of a bolt, but it's just got a different head shape for a countersink fit, or a counter bore is like a socket head machine screw. Really it doesn't mean their threads are any different. Like to say one's a screw and one's a bolt in this kind of world is kind of saying the same about the threads, but where you might get confused is you might call a screw like that really coarse thing for like a wood application. We call that a screw, and it has this really, it's made to like cut its own way through materials. Um, so don't confuse that kind of a thread relationship to maybe what we call a bolt, and we call it a screw as well. So it's just that hex head machine screws don't really cut their own threads. I mean, they need something cut for them to fit. And but there are different fasteners that we call screws that really are designed to cut their own threads. Like it's kind of built into the fasteners to cut its own threads. And so that might be what you're more familiar with calling a screw. So anyway, I just wanted to point that out, that you will see that terminology, screw terminology, used for a bolt. Don't get it confused that it can cut its own way though. So anyway, so let's see. So this width across the flats, max width across the corners. I need to know the head height and maybe what a normal clearance hole would be. Yeah. We'll talk about why that's. And I know I'm probably going to run out of time. If you have to take off, it's fine. I'll keep recording this to at least fill out the columns of all of these. And if you want to hang around until I do, that's fine. This will be like a 2-part video on just this worksheet, but this stuff definitely applies to how I need to fill out the worksheet to draw from. So width across the flats on a 1/4 inch bolt. If I go to this appendix, and I'm going to look for that now, I'm just going to scroll through what I do when I'm working on these problems. I'll look for like the imagery that goes with that type of fastener. So this is a hex head bolt. So I'm going to look for the images that have a hex head bolt. And so let me scroll down here a little bit. So these two, I don't need these two right now. It's actually the third page down is a hex head bolt shows up. Now I'm just going to look to make sure that this is like not metric, or that it's in inches. And this is a chart that's in inches. The size here, D, these are like major diameters, or kind of the nominal sizes. If I scroll down to the next one, maybe it's the metric version of this. Let me see. Nope, it's the nuts, or the internal type thread fastener that goes with those bolts, and these are all in inches. If I scroll down, it might be the whole group of these in inches first. Yeah, these are all in inches for a different type of fastener. Then even one more. Yep, we've got some notations there, some more. These are still in inches. Maybe it goes through all of the inches, including the washers that can potentially go with these. And then I finally, maybe it goes to metric. Yes, goes into metric fasteners here. So this is a metric hex head bolt. And then I should find those M designations. So I'm looking for a 1/4 inch bolt. So I'm going to stay up here. Mine's 1/4 inch nominal size, which is D. It doesn't even, it's funny, it calls that D but maybe it means diameter or whatever, but it doesn't even have like a D variable in the picture, but it would be the major diameter of the threads here. So We need the width across the flats. So it gives you this formula to figure that out. It's like, oh, the width across the flats, it looks like this. That's actually the tool that would slip over it. Well, it's they call it variable F here. And that means it's 1.5 times D, the actual nominal size, plus a little bit extra is what they have. So they've kind of come up with this constant multiplier that you would multiply the major diameter with, and then you got to add a little bit. When you're above quarter inch, you don't have to add that little extra little bit. It's only if it's a quarter inch size do we have to do a little correction on our formula, essentially, is how I read this. Like the 1.5 times D is pretty general for what it will be across the flats, unless it's a quarter inch bolt. That's gonna be a little bit small. And then the width across the corners we have, which is G, we have this other little multiplier, constant times F, which is the width across the flats. So in order to figure the width across the corners, you got to already know what the width across the flats are because it's part of the formula here. So here's your math formulas coming. Not that you know these formulas. Some engineers has figured these out for us as a general rule. So width across the flats, I need 1.5 times D plus that 0.062. So I'm going to pull this up, my calculator, and run my little calculation here. So it's 1.5 times the major diameter. So that's I did it divided by, let's see, 0.25, which is quarter inch. And so I get that this 1.5 times D is this. And then I've got to add that extra little bit according to their little table. 0.062. Oh, yeah, I might have messed that up. 0.375 is what I got. And then I'm going to add 0.062. Yeah. So they have that. If I really took a measuring tape or my caliper and I measured across this bolt head, if it measured 0.437, that would mean that I could classify this bolt as a quarter inch bolt at least, because the head is this, So 0.437, 0.437. So that's going to be the next one I need in my row here. 0.437. And then I got to know across the corners, maxed width across the corner. So I go back to that, and I think it's going to be, here's maxed width across the corners, variable G. G is what I just figured out times this other constant, 1.1547. So I've already got this in my calculator, so I just turn around and say, hey, multiply that by 1.1547. And this would be, especially if I was identifying it with calipers, great. If I'm going to draw it too in CAD, it's going to be this is maybe a measurements I would want. 0.54. I don't know how many decimal places. I think I held 4 decimal places. 0.5046, 0.5046. Whether you're holding like 2 or 4 decimals, I'm not super critical on. I mean, it might be more critical, but the head height is probably given on that chart as well. Let's see what it says. This one. This would be variable H that I need to know. So variable H right here, head height for a basic quarter inch is going to be 0.625 times the major diameter plus a little bit here. So it's this little formula for the head height. Okay, let me pull up my calculator. So it's going to be 0.625 is the constant times my diameter, which is quarter inch. And then that's not quite right. So it needs a little bit of a correction here. So I'm going to add 0.016 is what it tells me. So this to me, if I was identifying that fastener, would have this head height 0.1723, 0.1723. Yeah. That would be and now the normal clearance hole. Okay. So this one I might need to look at a different sheet, but it wants to know what a normal clearance hole would be is like, so this is a bolt. This is actually like an external threaded bolt or a screw, hex head screw. Let's say it needs to pass through something and then go into some threads. So a relationship where I might be bolting on a plate to something in group two, if I just, one thing I might pull up real quick is just the group two finished drawing. In fact, if I just go to this, our module real quick, it'll have an image of it for just so I can explain maybe why it's asking what a clearance hole would be. So group two drawing, you'll kind of draw this relationship of something going through something right here. You'll draw this one particular view. This is like 4 different views of stuff that we'll draw. It'll look like this on our drawing. This is nice because it's kind of zoomed in. But what we've got going on here is a hex head screw or bolt uh, going through. So these are 2 different materials. Like this is maybe a top plate being bolted to a sub plate. So kind of a relationship where I need to, you know, instead of like welding these two together, I'm going to bolt these two together with this fastener. So what it's going to do is this fastener is going to pass through this upper plate, and then maybe this lower plate is going to be all cut with threads that this fastener will like thread into, and then it will. I mean, this is a relationship if you've ever built stuff and put it together. This happens all the time. What you can't have when you do that is that upper plate can't have a hole that's like too big or too small for that fastener to pass through. It's like there's no threads in this one for it to go through. It's going to be held in place essentially by the threads in this and the relationship between the external and internal threads that are holding it together. And then just the head of the bolt itself is what holds this thing so it can't fall off, right? So what we have going on there is a clearance hole through that upper plate. And we'll draw that relationship here this week, but and so that's a real specific thing too. Like we don't just guess like, oh, I would just make it a little bit bigger so that thing will go through. Well, there's actually some engineered design in here. A clearance hole can either be loose, tight, or and so let me go back to this our worksheet here. What it's asking for is a normal clearance hole. So maybe I can have loose, tight, and normal. So I'm looking for normal clearance hole size for a 1/4 inch kind of hex head screw or hex bolt. So let's go look at this, our index here. I don't think it's on the same sheet where I found everything else. I think there's a whole sheet designated to clearance holes. So I just don't know where they are. I think from here on, we just go through a bunch of specific threads and then we hit those metric ones. Let me just make sure it's not right before we move to metric. So if I just page down from here, nope, we go into metric fasteners and then all their specifics. It must be after all of the like fastener designations. And then we get into clearance holes. Yes. So it's like page 17 is what I'm at. We have inch clearance holes and then we have metric clearance holes. And then it's right before the end of the appendix and then whatever else I added on at the end. So really it was kind of the last 2 pages of the appendix before it goes to appendix C references. I should have just booted out this page. You don't even really need it, but um, yeah, right before this page, we have metric clearance holes, which are kind of fitted by normal, loose, and close, or normal, close, and loose. And here's the inch clearance holes for normal, close, and loose. So it just wants to know, hey, if in that upper plate, how big would I need to make the hole so that the bolt could pass through it without and it would say in a normal fit and 1/4 inch. Well, then I need to make my hole 9/32 in diameter. This is again like it's got the numbered style, like smaller fasteners, smaller than a 1/4 inch fasteners. And then it's got from 1/4 inch and bigger is kind of fractional. So kind of numbered size screws and bolts with fractional sized. I'm looking for 1/4 inch, I believe. So it's 9/32 would be my clearance hole to pass through on my worksheet here. So normal clearance hole would be a 9/32. Yes. Sorry. That would have said 9/32, I think. I'll check it real quick, but I think that's what I determined. 9/32 right there. Yeah. So that's that one. I'm gonna keep going. So they all have just a little bit different twist in what the information is that we want. This one is still, this is hexagon socket head cap screw. And I'm hoping this terminology is the same thing in and these are inches here. So I'm gonna scroll up again where the above the metric fasteners, and it's like a hexagon socket head cap screw is this one for sure. There's the one we used, then it went down to the nuts, which we're not doing yet, and then to the next page here on page 5 of the PDF here is hexagon and spline socket hex cap screws. But this is probably going to be where I'm going to pull my data from, this particular data sheet here. So let me go back. He wants to know the major diameter. It was already given to me. It's 1/4 inch. You just give it as a fraction again. It wants to know the max head diameter and the max head height. So this must be something that's specific to this type of fastener. So the max head diameter and max head height. Okay. Yeah. I would need to know these to so these type of screws can either be inset, like if I go back to this just to talk about like how they might be used. A lot of the times these go into a counter bore, and we've drawn a few counter bores and we've notated a few counter bores on our drawings already. This type of screw might fit into a counter bore to where it's gonna like all of this is going to be doing all the work. This might be sunken into the material, and so that when my fastener is actually applied to the, is doing the work that it's doing, it might be that the head is actually like flush to the surface. So I don't know how to explain that other than like this. Like we've drawn this kind of relationship. That means that my head isn't going to sit on top. Like a hex cap screw kind of has to sit on top and it has to protrude from the materials that it's like hooking together. Well, this is a situation where I don't want that to happen. So I'm going to use a different fastener so that I can sink the head into the material. And then I get this like and then I get this nice flush finish with my fastener sunken down to the material. And this is really common in automotive. You'd see this a lot as a way to sink the fastener down into the material. And so I don't have a protruding head. And then I feel like a lot of the reasons why I would use this one is maybe the torque load that they can handle is much more than maybe a countersink, which does the same thing. I think this is a poor drawing of a countersink. Usually that is seems like a very minor countersink. I think they have a better drawing. Like, I don't know. I thought they had one. Not really. They're like this is a better drawing of a countersink. Like that head also, if it's the different type of a flathead machine screw rather than a hex cap screw or a socket head. It's also designed to fit flush, like a flush finish and sink the head into the material. Maybe the torque load on this is less than on the socket head style, but I'd have to look at the engineering specs to see. So I do feel like these are a more torquey situation here. Anyway, I'm going to go up to the inch ones where we're actually going to pull the data from. This one, the sheet 5. And so I don't know. I'm on a 1/4 inch though, and so it's chart. Let's see here. This is the hex jam nut. So this is different. Just look at the headings over this. These are nut sizes. I need to get into these charts right here for this. This is going to be for, I think it's going to be spillover from these jam nuts and these hex nuts. Actually, isn't just on this page. It's the first half of this page too. Hex jam nut. Okay, so I'm going to skip that and go down into these charts. Mine's 1/4 inch again. 1/4 inch. Actually, this chart's a little more simplified, really. From 1/4 inch to 4, I've got a pretty constant like way to figure this out. So here's my head diameter, which is A. Whether it's a spline fit or a hex head, ours is a hex head, but I think they're going to be the same anyway. It's just 1.5 times the diameter, which is the major diameter of the shank here, of the shaft, actually. So if that's 1/4 inch, I'm just going to times 1.5, and that's going to be my max head diameter. 1.5 times 1/4 inch. So I think I already did this before, but let's do it again. Bring up my calculator, right? It's 1.5 times the major diameter, which is 1/4 inch, 0.25. So that thing has like the socket head on it. That's max diameter is going to be 0.375. So back on my worksheet, that's 0.375 right here. That's critical because in order to design around that, I have to have a clearance hole bigger than that for that head to fit into, right? Like this is usually designed to fit into a pocket on a part. And so if I'm going to design my part, I'm going to design it so that it's bigger than this. So it fits in there. And there's a tolerance applied to that. It's kind of that clearance hole type tolerance apply application. Then the max head height should be on that same chart. Max head height is just equals the diameter. So that's kind of nice. So as long as I know the major diameter, I already have the max head height. So this actually matches the diameter. So it's 0.25, the H. Yep, that's my next chart, 0.25. And then the normal clearance hole on that, I just need to know that based off the major diameter, 1/4 inch, and that normal clearance hole sheet. So I'm going to go down to it here. It's a little bit further down beyond all the fasteners before that Appendix C call out. So before this is going to be clearance holes, normal for a 1/4 inch. It's actually the same, 9.930 for the problem I'm working, which is the same major diameter. So I say that's 9/32. The counterbore diameter, that's that clearance, and the counterbore depth, these matter. So that's just if I'm gonna sink this thing into the material, I need to know how deep to count or how wide to counterbore it and how deep to counterbore it. I can't say this is, I think this is probably why I've added some additional data sheets at the end of this appendix. I feel like this wasn't quite clear. Let me double check that though. I'll go back to my appendix B up to that fastener real fast, which was above the metric ones. So I'll show you maybe it is. I just haven't done this for a bit to see if it's explicitly given. So here's where I was at least pulling the data. It doesn't really give me anything else to work from here. I'm looking for how this fits into something. So this next drawing down, I think just below this, next sheet down, is potentially, hopefully, this looks like what it's fitting into. Like this kind of looks like the counterbore diameter, where I'd find this counterbore diameter. I think this works for some, but maybe it doesn't work for all. And that's why I've added some below. But let me see this. So this probably is correct though. Here's my 1/4 inch nominal size. The drill size A, which would be how big I need to make this, depends on if I want a close fit or a normal fit. Those two are calculated. What I want is the counterbore diameter and its depth. And I feel like it wasn't given here. Like it is given the diameter, but I'm not given like any kind of variable to solve for how deep that is. So B was the only thing from their charts that I was able to solve. That's the counterbore diameter, which is what they call out right here, 7/16 counterbore diameter. So I can add that one to my worksheet. For the counterbore diameter is 7/16, I think. Yeah, 7/16, not point. Sorry, 7/16. And the counterbore depth was, I feel like it was never given. It's funny that their own questions. I didn't add this to the questions. Their own questions had this. They didn't give me the data to figure it out. So what I did is towards the end of this, after the Appendix C page, let me come way down here. I just feel like it was missing. There's the metric ones, and they still don't give the depth either. So where I went back here is I think there's some counterbore size chart. And so this first one that I've added, which is yellow and green, it actually gives some counterbore depths, which is kind of critical based off, it looks like I have some inch ones and I have some metric ones all on the same chart. So this is just another chart pulled offline. Ours is 1/4 inch. It pretty much matches theirs because they said I'm 7/16, which is 0.4375. Their chart is out to 3 decimal places, so that rounds that 4375 up to 0.438. So this is correct. Like that's the same diameter in my chart that I found, and I can zoom this in a little bit. That's pretty small. So if I zoom this in, I'm looking at 1/4 inch. Really, from their appendix to this, it's the same here, but this is the one that's given here that's not given on theirs. How deep that head goes is 0.281. There's a few ways you could interpret that from these charts, right? Because the head depth was given as the same as the diameter of the major diameter. If it's 1/4 inch, then the head should be 0.25. So this, what I like about this is it shows that it's just slightly oversized. So it's not that this is a great example, but this is a little bit more than 1/4 inch, meaning that generally with counterboard relationships in like fasteners to the from fastener to what it goes into. Sometimes there's a tolerance allowed that we sink the head just a little bit beyond flush. And that would make sense here. This depth of this pocket is 0.281. And let me go back to my sheet and fill that out. What's that? What I was just saying is this is actually about the same number. Yeah, like ours says 7/16. This is 7/16 if it was rounded to three decimal places. 7/16 is 0.4375. So you got to know your decimals to fraction equivalent. The other chart gave it as a fraction, I think, if I go up to it right here. Um, and on this next page down, because this is like what the thing is going into. Yeah, it gave it as a fraction. And I just know in my mind that 7/16 is 0.4375. And so I can recognize that on that chart that it is the same number. Yeah. And the countersink diameter is different. They're definitely a different type of fitting in general. But and like I said, I don't love this. It looks weird to me. But anyway, so that is that one. But they are. Oh, I don't know what else is different about the next one. So this makes sense to me. I know that the max head height is going to be 1/4 inch. I'm gonna counter board just a little bit beyond that. It's the difference of like, 0.31 that I'm deeper. So I'm like a 30-second deeper than the head height. Because you would never want your head to be like just slightly above the surface. You'd rather it be slightly below the surface. Equal to or below it would be ideal, not above it necessarily. There's a reason why you're usually counter boring or counter sinking something, and that is to get it at least to flush, if not below flush a little bit. So that's why this would make sense to me. I'm actually gonna bore out the hole a little bit more than the head height. So that's never going to be above it. It'll probably rub on something, or there's probably some reason why I need my fastener to be below the surface level. So anyway, which is why we have these different fasteners. What's the next one? Hey, I'm getting there. It's probably similar to what I just did. Maybe I don't need to go through it. Oh, it is a countersink one. I guess I better do that. Flat countersunk hex cap screw. So if I go to my charts here, I'll zoom out just a little bit so I can zoom through them a little quicker. But we haven't seen countersink ones yet. We've seen the hex cap screw here, but I'm looking for a countersink version of that. Here's at least maybe some of the profile of what it would go into, but let's go the next one down. Maybe this is it. Countersunk head cap screws. I would say this is a countersunk hex head was what I call this one, maybe a spline head. But this should be the chart we're going to go to. It's in inches, yes. Ours is probably a 1/4 inch again. I don't know. I seem to I'll chart everything that I get to size is for 1/4 inch. Probably the easiest one to do too. It's 1/4 inch on the first one as well. So that's the major diameter. That's easy. You just say a 1/4 inch. Pretty redundant. Class of fits normal. Okay, so max head diameter. Well, let's go back to my chart here. Let's see if they give me anything to go with the max head diameter. They don't, yeah, it's A. A is the variable on that chart. So A, the max head diameter from anywhere from a number 4 up through a 3/8. So ours fits in here. We're 1/4 inch. You have to know where you fit in here. They've simplified this chart, from a number 0 to number 3. We'd have to see a table. And then it's this little table here. For number 4 is up to 3/8. Ours is 1/4 inch, so we fit within that range. 7/16, above 3/8 is this one, and then above 1/2 inch we have this one. So 7/16 is kind of a weird outlier. And it's not a widely used fastener size either. It's funny, we use 3/8 and 1/2 inch a lot. 7/16 is a real particular fastener size, but we have it. Ours fits in here though, so in order for me to figure out my max diameter, it's like 2 times the diameter or the major diameter. So 2 times 1/4 inch for me, plus a little bit of this what I call is a little bit of a fudge factor here, plus 0.031. So 2 times 1/4 inch should be 1/2 inch, but let's just pull up my calculator and do it like I would. I'd say it's 2 times, and then I lose everything. Back to my calculator. 2 times 0.25. And then I got to add a little fudge factor, 0.031. Excellent. Thanks. Yeah, thanks, Stacy. Yeah. 0.531 would be my diameter of this countersunk 0.531. Trying to look to see if seems like depending on which chart you go to, you might come up with a slight different, I do feel like they have a few charts in here that might be slightly different, but I'm going to go with 0.531. Let me know if you're looking at a different chart, but 0.531. There might be a chart that just calls that 0.5 without that little added. But this is what if I'm using that chart that I have, that's what I come up with. The max head height is on that, right? It's going to be H. H is even this. Oh my gosh, I've got to use cotangent. I've got to use some triangulation. So, which is fine. I can just do this on my calculator. For those of us that haven't done trig yet, we might not recognize this is a trig function, cotangent of 41 degrees. Which is because this is 82 degrees and half of that. Okay, it gets a little complicated. It's like triangulation to figure out what that is what they're using. But there might be a chart where this is called out more explicitly without using this potentially, even though this would probably work. Let me see let me see if I added on one that's a little bit more simplified. I think all of them. Yeah, this okay. So here's a little bit of a difference. Here is the different bit that fastens these down, whether it's an Allen head or a hex head bit or a spline head bit. What if it was just a slotted fit? I don't know if our chart acts. Let me check this real quick. This is where I could mean that it doesn't say whether it does say flat countersunk. It doesn't say whether this is slotted or what type of bit is fitting into it. So that's why I feel like you could also have used this chart and you would end up with only 0.5 instead of that little extra added on because ours is a 1/4 inch size. So what I mean is there's kind of two charts that go with this type of kind of flathead machine screw, depending on what type of like bit you were using to tighten it or loosen it, whether it's splined, hex head, or slotted head. Maybe, well, this does say flat too. Okay, I was just wondering. Anyway, yeah, so I feel like that's why you could come up with a different answer on this one that I just did right here. Let me just back up and you could either come up with this 531 if you use the first chart I did, or it could just be 0.5 if you were using that second chart. Either one are correct to me. Let's see if this max head height is easier to calculate on this other chart though. I can't remember for sure, but it seems like I've picked through these enough to know that there's some real particular things about them. Yeah, really, they give you this as maybe a simpler, like it's still solving for the head height here, kind of how deep I've got to countersink this. It's 0.596 times the diameter. So this one, technically, this to me is a little easier than doing this formula. They probably come up with about the same, plus or minus a little bit. And so I'll use this one. Realistically, if I pull up these fasteners on McMaster car, they might have subtle differences too, based off that bit that's going into it. Um, yeah, but I'm okay with use either one, especially if it's an easier formula, then use it. So I'm going to use 0.56 times 1/4 inch as my head depth here. It's 0.596 times the major diameter, which is 0.25 or 1/4 inch in decimal form. So I have this head height as being like a 1.49. And I haven't done the cotangent one. If anybody does it, let me know if it's about the same, or it's probably going to be varying just a little different. And but I'm okay with this one. It's an easier to work with formula. 0.149. Yes. I still got to figure out the normal clearance hole, the countersink. I feel like why that varies from that one chart to the other is just that bit that's going into it. They're probably one is probably just subtly deeper because just the requirements of that type of bit to go into that head, they needed to probably increase the head height a little bit or lessen it a little bit. So that probably has changed over time based off the kind of bits we're used to using. And we seem to be, in the modern world of fasteners, we seem to have introduced quite a few different bit designs in the last 15 years, 20 years even. We've gotten a lot more. We just have, I think we have a lot more variety of types of bits for different applications than we used to. Used to just be Phillips or flathead was about it, right? But now it's way more complicated than that. But that affects the design. It affects the head depth and all that a little bit. Subtly different, but has to be figured. Normal clearance hole is what I'm looking for though. Quarter-inch normal clearance hole. It's going to be the same as this one for sure. It's going to be 9/32. I would use that same chart to find it. So I already know that one. So you can sometimes use, and I keep putting that. I keep thinking that it's 9/32. Countersink diameter and the countersink angle. So those are going to be what it's going into. These are kind of confusing. We've already done the fastener itself, head diameter. So this is more like this one. We're talking about what it's going into, its diameter. It's going to be slightly bigger than the head diameter. And the countersink angle is going to be the flathead machine screws that are countersunk, they can be at different degree angles. So let me go to this chart and see what's the next page down from here. I don't know. Let's see. It's washers. I feel like the best picture of that is that one, like this one, but this one is metric. So there's one above it that's standard. It has the same kind of call outs. It's probably above the charts we were just using. This one, this page right here. It definitely has the diameter. C is going to be the diameter for that head. And so if I'm on quarter-inch, the one I'm doing, but it's a countersink head diameter, this is how big it's going to be, right? It's going to be 0.278 in diameter. It's got to be bigger than 0.25, or it's got to be bigger than the head. Does that one make sense to me, though? Let me see. Counterbore B, counterbore C. No, it didn't make sense to me. That's why I hated this. Because to me, we already know the head diameter is a half inch at least, or 0.531. So the counterbore diameter has to be larger than. So this to me was a confuse. I knew there was more than one reason why I didn't love how they've designated the counterbore diameter or the countersink stuff here. And it only gives me half the stuff I need here. So I felt like this was kind of a failed, in some ways, this was a failed chart to me to figure out all the stuff I needed. So I think I'm going to go back down to that red that yellow and green chart that I've added. I think it explicitly just gives me the numbers that I need to work with. This one, because it's counterbores. Maybe I have a countersink one. Maybe I'm wrong here. This is only counterbores. I'm looking for countersink. So did I add a countersink one? No, that's an oval head. Really weird fastener there. Round head. It might. It might be this one. Maybe this one is better. I just feel like that's metric. I feel like they did better with their metric charts than they did their standard ones. I do remember that too. I'm trying to think of what I think. Well, it helps me if I look at my cheat sheet here. Look, I have this big like red line that says not on chart. So it really wasn't able to figure it out. Yeah, that's good to know because and I feel like we've kind of done that. We found that out ourselves that it's not explicitly given. And what they do give us doesn't make freaking sense. Because if you just think about it logically, this diameter to fit this thing has to be this diameter at the top. But it has kind of it's kind of weird because it has two different diameters. I mean, it has like an angular measurement with it too. So my way of helping you solve that is like if it's not given, it's just not in the chart. And that one is not in the chart. And what is given in the chart does not make logic sense per se. This one here. This makes zero sense because it can't be 0.27 in diameter. This thing is like a half inch in diameter. So It's kind of weird. Maybe that's down at the bottom and then it's out to this degree is the way they're reading this. I don't know for sure. And and this is also a 60-degree fit, which is kind of odd as well, but that's really, I don't know. I don't know. There's a lot. This is kind of strange here. So proceed with caution on that particular page. So I kind of skipped that one, or I said at least has to be, I mean, like to me, this is like not clear. So you could just say NA. But if I'm saying it's anything, it's got to at least be zero point 0.5, if not 0.531 in diameter, because that's the head height here. Like it's going to essentially it's got to match the head diameter. The countersink angle, I think, is given on the actual, not on this one, but on the actual head of the bolt itself or the screw. Let me see. That's right here. Like they give you that this is 82 degrees plus or minus 2 degrees. Let's see if it's the same on the next one because I know that's that specific or that specific bit type. But let me see the next one down. I think it's the same, 80 to 82. They kind of give it in a different way, but so I could say it's like 80 to 82 degrees essentially. Or I could say that it's 82 plus or minus, which would really give yourself what, 80 to 84, really? Anyway, that could have a couple different answers depending on which chart you're looking at because it varies depending on which kind of bit is fitting it. But anyway, a lot of things that could be cleaned up. So what is it? If I really captured the entire range, it's like 80 to 84, 80 to 82. Really, the industry would call that an 82 degree. It's pretty known that that's like an 82 degree. I guess you could put degrees or whatever, but something like that. Then like it's 80 to 84 degrees. They make different like those machine screws do come in different degree increments of how they mate to their counterpart, and how that because when that fastener goes into its material, this is kind of what's contacting and kind of holding the load in some way. Like that is the mating surface of the countersunk material that it's going into. I don't know if we don't totally draw that relationship. The only one we really draw is like a hex head bolt down through two parts. But yeah, that is like a mating surface, that 82 degrees. So when someone has to cut that to sink that head into the surface, they have to cut that accurate degree pretty close so that the entire surface of the bolt mates with the mating surface. I wouldn't want there to be like some voided gap, like somebody done a 60-degree included angle, and then I put an 82-degree head in there. I don't have the relationship that I need where that angled surface of that fastener really wants to sit in. I feel like it needs to seat nicely right up against the material that it's holding against. Otherwise, the design intent is not there. So, the degree of that I construct or machine my part to has to match my fastener. And there are a few different degree increments they use for these particular fasteners. So I have to be careful, order the right parts to match the right setup. Because the idea is this surface needs to contact its mating surface completely across this. Yeah, I don't know. Let's see. I don't know. Let's. Let's see. I don't know. They call it 90. Yeah, yeah, yeah. There you go. So 90 plus or minus. Yeah, yeah. So you're right. That thanks, Metric, for keeping something with the power of 10 capability instead of 82. 82. I know that's so weird. 82 being the really common inch one, though. It really is. Yeah, we'll just say 90. How about that? What a brilliant concept. This is like if these 2 points came together, it's 90 degrees essentially. We'd call that an included angle. It means really this is half of that. It's about a 45-degree angle. The same with the 82. It's like a 41 degree kind of. So what we're looking at is what we call as an included angle, both sides included together. Yeah. Yeah. Why don't they all just 90? That makes more sense. You're right about that. That's funny. Okay. What else on this sheet? I don't know. This can go on forever, huh? We got one more sheet. Oh my gosh, we're gonna get there. All metric here, probably the same stuff. Yeah, yeah. So it's about walking through the same. Um, Maybe I don't even need to do this. Maybe I can just say, oh, I mean, I can do one, but we got a counterbore, we got a countersink one, plus we got one that's just an actual hex head bolt. So we're looking at all kind of external features like we were hex head bolts, socket head cap screw, and then a countersunk one. So Essentially, we have one. Yeah, I don't know. I'll do. I think we're getting better. This is going to be a 5 millimeter. I think is how I would call this out. I don't have to put the M5. M is for metric, but 5 is the millimeter size of the major diameter. The max width across the flats. In fact, I think this will find that these charts are probably easier to use. Maybe they're more explicitly given without a formula. Let's just see that. So I'm going to go to the hex head metric right there, metric fasteners, hex head. It wants to know the width across the flat, so that's S. We're a 5 millimeter bolt, so we're right here, 5 millimeter screw. Hey, yeah, it doesn't even give me a formula. What I like about the metric charts, they just spit me out the numbers. So I would say the max width across the flats is 8. So I'll fill that out and just poke along. I mean, this can be nice if you actually like probably put these up on. I should have probably done this a while ago. Just put them up on each screen here. So you can see where I'm looking, where I'm filling out. But across the flats is 8. That's just 8 millimeters. Sure, you could put a 0.800, whatever's called out in the chart, or just 8 is fine. Max width across the corners is the E dimension for M5. E is 9.24, so I guess I'll carry 2 decimals for that. The max head height, that's K. So I like that this one just gives me it's 3.88. Thread length for a screw that is shorter than 125 millimeter. I wonder, it must be here. Yeah, yeah. So what we have here is B, this length of if this bolt length is shorter than 125 millimeters. So what I have is bolt lengths that are less than or equal to 125, greater than 125, and less than or equal to 200, and then bolt lengths that are beyond 200 millimeter. So it says for a screw that is shorter than 125. So I'm going to be in this column. It's only going to have 16 millimeters of actually threaded shaft, and the rest is just going to be smooth and match the major diameter essentially. And so it's 16 is what I have here. Thread length for a screw that is shorter than 125. It's in an M5, it's 16 millimeters of thread that I get. That kind of matters because when I'm passing through something, um, if this is not threaded here and I'm passing through a thinner plate to a thicker plate that's threaded, then if it's not threaded all the way through here, then I may have an issue where I don't actually engage the threads, right? So I have to be aware of when my fasteners are threaded all the way through or not threaded all the way through. And that can just vary on length. Usually what drives that is the length. The longer they are, they start to not put threads all the way through them because they generally think you're going to pass through something of some thickness and you're going to go into something that is threaded. And so the need to have the entire thing threaded is not. And it's just a cost savings thing that the fastener manufacturers can speed up they can speed up the manufacturing time to be like, I only need to thread 16 millimeter. I only need to thread 22 millimeter or whatever it is, right? Like it's just like a speed thing. You just have to be careful when you're designing around that you don't end up designing around something that isn't threaded all the way. And then it's pretty common that if you need one that's threaded all the way, they're just going to be a little bit more expensive probably. And then you might be limited to the longer they get, like I said, the longer screws get, bolts get, it's more common to find that only they're partially threaded. The shorter they are, they're usually fully threaded. So just watch for that. It's just kind of a thing. And they show that clearly in their drawing. When we draw ours in group one, I just drew them all as fully threaded. And I really referenced that because I went to McMaster Carr and I just looked at what the common, what was funny is when I looked at these drawing assignments before I landed, I noticed they were doing this. They were doing partial and full threaded when they drew it. And I was like, well, is that right? And when I went to McMaster Carr and pulled up our actual hardware, everything that we actually draw in group one is all fully threaded. If you were to go buy it, there wasn't even an option to buy partially threaded. They're all short enough that they're fully threaded. So anyway, it's another thing to note on about hardware. So normal clearance hole for this M5. Well, I'm gonna have to go to the M5 clearance holes, which is close to that Appendix C sheet. It's like right before that Appendix C sheet, right? Yeah, you can use Control Find, do whatever you need to do to navigate this. There's the inch clearance holes that we've used a couple times, here's the metric clearance holes right here. So it says for a normal clearance hole for an M5 right here. This is my row. M5 normal is 5.5 millimeter. So I'm going to oversize that by about a half a millimeter to pass through it. 5.5, sorry, 5.5 millimeter. That's that one. I got two more. Let's do them. Major diameter. This is 1.6 on an M1.6. The major diameter is 1.6 millimeter. The max head height. This is a socket head cap screw. So it's probably the next sheets down from the bolt one we just used, right? There's hex head, metric. Next one is the nuts for a metric. But here is the socket head cap screw metric. So I'm a 1.6 millimeter. So it just says, oh, if you're a 1.6 through 2.5 millimeter, you need to see this table. So then it has this max head. I'm looking for max head diameter. I'm actually looking, yeah, max head diameter first. So I'm looking for it's kind of weird how they've given this. It's A. I'm looking for A. It says see table for A. Okay. The max head diameter for 1.6 is 3 millimeter. Oh, that's sweet. It just gives it to me. I don't have to do any calculations. It's pretty common with these sheets. There's no calculating. Max head height is H. So they say that the H is going to actually equal the major diameter. That's kind of like in the inch one was that way too. So I'm going to say the max head height is 1.6. A normal clearance hole on a 1.6. I don't know. It's down on this sheet, clear down here. Clearance hole for a normal fit. M1.6 is going to be a 1.8 millimeter hole. That makes sense. It's going to be slightly bigger, 1.8. I need to counterbore this thing with the counterbore diameter and depth. This one is for sure that green chart that I have added on here. It seems to be maybe the most reliable just to spit out the diameter and depth in one. Here's 1.6 diameter hex cap, or it's a cap screw. It's a counterbore, so we would know that this is like a socket head, but counterbore diameter is 3.5 millimeter, which makes sense. 3.5. That's a half a millimeter bigger than the max head diameter. So that makes sense. That's definitely oversized. My counterbore is oversized to accept this pretty easily. And then the depth of that to sink it, well, I hope it's deeper than 1.6 millimeter. Let's see. It's 1.95 millimeter. So it's definitely like sinking that head in just so it's just below surface flush. Yeah, that's that one. We got one more, right? Yes, the countersink style, the angled one that we know is going to be, we already determined that's going to be at 90 degree. We just looked that up. It's 90 degrees plus or minus 2. Is that what it said? I'll look it up for sure, but I'll at least type it in. And I'll come back and put the range in, but it probably has the same issue on countersink diameter. It's got to at least match the major diameter, if not be a little oversized. So M16, that's a 16 millimeter screw there. The head diameter, let's go look and see if it shows me this. So what I want is this one here, right? This is a hex head type. Let me see what else they got for metric though. I just want to explore these sheets just a little bit. So they got the socket head that goes into a counterbore style. They've got some of that stuff that's not super reliable, but here's the countersink head, 90 plus. Actually, it's minus none plus 2. So it's 90 to 92 is how I'd read that tolerance, but for that degree. But A being the diameter, let's see what it gives me here. A and then the head height. Maybe these are better, more reliable than they were for the inches ones. So the head diameter for a 16, M16 by 2 pitch. So I don't really need to know that, but because I don't know which pitch I am necessarily, whether I'm coarse or fine. But it's 33.60 is the theoretical head diameter. So I'm going to type that in. 33.6, yeah. And then I'm going to say that head height is maybe given here too. Yeah, H is explicitly given that it's 8.8. Yeah, I think so. These are in millimeters. Oh, for some reason I have that in red. I don't know why. Probably just I don't know why. I think it's because like I end up doing some equation. There must be I don't know which one I'm referring to that is either variable h or y. So I think it depends on which chart you use, whether you're choosing this chart or there's probably one more chart. Um, well, y is definitely going to be what it goes into. Yeah, I'm not sure why. I'm not sure why I would have used y on that. I wouldn't have. Okay, I'm just gonna keep going. Don't. I'm just gonna use that chart information. That's good. Now the normal clearance hole, I definitely have to use. I'm looking for an M16 or a 16 millimeter diameter, and I'm looking for these metric clearance holes. So if it's passing through something and it's an M16 for a normal fit, is this normal fit? Yeah, normal. It's going to be 17.5 millimeters in diameter. That's 1.5 millimeters bigger than the major diameter there to pass through. And then the countersink diameter. This one might be a little bit more accurate. This one I think is yeah, 33.6. So it's either the head diameter or let me see. I think it is. Like let me see here what it has for Y. This is definitely what it fits into. And when you're thinking of the countersink diameter, it's kind of like what it's fitting into. So Y for an M16 it calls out 33.6. When I look at my chart, I think, well, that's the exact size as the head diameter. So this could be an issue. It's what's right according to this chart. And I don't think I have a better chart to show that. Um, yeah, I think that's the only chart that it shows it. There might be one. I have a couple numbers on my cheat sheet. Like there is another chart that you could pull that data from. I can't remember where it is. Let me see real quick. Could be this one. If you were pulling this one, um, you you might have pulled that it's like an 18.2 diameter for the countersink diameter. That would be okay too. That would be what I would actually um, put. Is that right? No, it doesn't make sense again. It's kind of weird. Yeah, 33.6. It's like this one is definitely made for almost like a countersink head that doesn't this I don't know. I can't it's 60-degree included angle too. So it's a totally different like fit type here, which I can't say I've pulled some data off that chart, but not all of it. I've had to be careful. I've used some of the counterbore diameter, but I've really skipped it and gone to my yellow and green chart. Yeah. Okay. And that one just says straight up 90. So if you just kept this 90, that's fine. It's either like 90 to 92 is what I'd really think of the range if I was looking at both those charts. But and that finishes up. That's it. I mean, they're kind of painful. Ooh, they are a little bit. And I think there's a few variations you could find. And if you find them, if you go through those charts and you find that, oh, one says this, one says that, it's okay either one you choose. Just like I've showed you that there's a few that conflict each other just a little bit, but and I thought for sure I'd maybe I know I put the counter bore chart in because I felt like I was just frustrated that they didn't quite match. And then or they didn't give me the depths is what was frustrating to me is that they asked for the depths, but they didn't give it to me in the chart. I thought I included one for countersink, so it was a little more clear. Um, I think I need this one when I go to draw ours actually, but yeah, I thought for sure I'm gonna have to look for a good countersink chart to kind of take the place of what is a little bit confusing in these ones. So anyway, that's it. So I'm gonna wrap that up. We'll actually start drawing at some point. We're actually are kind of ready to